We will revise AEC module number 2.2 revision, and that will be MOSFET DC analysis. MOSFET DC analysis. Okay, so basically we will be using the term biasing. So in BJT we have used this term biasing to set up VCE and IC. So in case of BJT, now let's consider a NMOS, enhancement channel NMOS, N channel NMOS, gate, drain, source. So we will set up VGS, VDS and ID, current ID. Alright. So what do you mean by biasing in terms of BJT? Anyone? Biasing means you set up VGS and ID such that your MOSFET works in saturation region. Okay, so your MOSFET should work in the saturation region. In a morning session I have discussed in revision module number 2.1 revision, I have discussed where is the saturation region for a MOSFET. So if I draw the transfer characteristics of the MOSFET, I'll locate the Q point. This is ID, VGS, and how is my curve looking like? My curve is like this. Okay, and if I locate the Q point over here, fine. So this is my VGS Q and this is my ID Q. Okay, this is how I locate the Q point in transfer characteristics. I can also locate the Q point in output characteristics. So if this is my ID, if this is VDS, how my graph look like? My graph looks like this. Okay, and I take the Q point, I'll draw the DC load line and I mark the Q point over here, let's say. Okay, if this is my, let me draw it properly. Okay, so if this is my Q point, so this is actually Q point. So this will be VDSQ and this will be IDQ. Okay, so and this region of operation is saturation region of operation, right? So this region is saturation. Alright, so this is again my Q point. So I need to operate the MOSFET in this, need to decide the Q point such that the MOSFET operates in the saturation region. Are you following, everyone? Clear this so that I can move on to the next one? You have all understood what do you mean by biasing? Setting up VGS and ID such that MOSFET works in the saturation region. Is this clear?
Yes, sir.
Okay.
Yes, sir.
We'll go to the next point. Please write down depletion MOSFET biasing. Depletion MOSFET biasing. Okay. Now, in the morning session, we have discussed depletion type MOSFET, right, can take VGS value which is 0 or negative or even positive. You have drawn the characteristics, right? And what is the equation for the current over here? ID equal to IDSS 1 minus VGS upon VP the whole square. This was the equation, right? So these things you should remember. VGS can take values of 0, negative and positive, and this is the important formula. But this is for depletion type MOSFET biasing. So there are 3 types in it. First type is 0 bias. Second type is self bias. And the third type is voltage divider bias. Voltage divider bias. So over here in 0 bias VGS will be 0, VGSQ will be 0, here VGS will be negative, and here in voltage divider bias VGSQ will be positive. So hence we have 3 type of biasing techniques. Are you following up till now, everyone? Yes,
Yes,
no?
sir.
Okay. So if I am going too fast, please stop me. I'll slow down. So let's start with zero bias circuit. So write down a zero bias circuit. So this is using NMOS depletion type. It's very important to write that. And what's the symbol? Symbol is like this. You have to mark this show this channel that it is present. And this three terminal symbol. This is drain, gate, source. We have four terminal symbol also. This is gate, drain, source and body. So this is NMOS D type symbol. Okay. Now we draw the circuit. Fine. So please draw. I am using the four terminal symbol. Please draw the circuit along with me. So you take the MOSFET. Listen carefully. Mark the terminals as gate. This is drain, and this is, let's say, source. Okay. So out of this, your drain terminal will be connected via a resistor to RD, VDD. Resistor value is drain resistance, that is RD, and your gate terminal will have one resistor RG. Its value might be very high, and this is going to the ground. That's it. This is my circuit. And in this circuit, please mark the following. You will mark VGS, you will mark VDS, and also you will mark ID. Can IG current flow in a MOSFET? Can IG current flow in a MOSFET? No. Why it cannot flow? Because of presence of oxide layer, right? So IG is always 0 amperes in case of MOSFET. But still we are drawing it because we need to apply KVL, KCL. Up till you understood? Can we start? Can we proceed ahead? Yes or no? Yeah?
Yes, sir.
Okay. Now we apply KVL to the gate source loop. So this is my gate source loop. Okay, yellow color. So what is it? KVL to gate source loop. So what do we get? Minus IG into RG minus VGS is equal to 0. Now IG for a MOSFET is 0. Why? Due to SiO2 layer. Okay. So Ig is 0. That means what? VGS is equal to 0. And I've told you, this biasing is for zero bias circuit. So VGS is equal to 0. Even if VGS is equal to 0, still the current exists in the circuit. So what is the current given by? Current in the MOSFET given by ID equal to IDSS 1 minus VGS upon VP the whole square. Okay. Now over here VGS substitute as 0. So what it will be? IDSS into 1 minus 0 the whole square. So what will be ID? IDQ, this is VGSQ. What will be IDQ equal to? IDSS. Got it? So this is my Q point. Yes or no? Hello? Did you
Yes, sir.
understand? Okay. Next, I'll apply KVL. Next, I will apply KVL to drain source loop. So I'll draw the drain source loop over here. This is my RD. Then I have the MOSFET. Okay. This is my MOSFET. I'm not interested in the gate side. And this is my VDD. So now I'll apply the KVL in this loop. So I have to mark over there VDS and ID. So what do I get? KVL to the drain source loop. VDD, you're going from minus to plus, so positive. VDD minus ID RD minus VDS is equal to 0, correct? So from here, what is VDSQ? VDD minus IDQ into RD. Got it? Okay? Understood this much? You have completed up till here?
Yes, sir.
Okay. Okay, great. And if someone tells you find the value of VD, what is VD voltage? I mean that this much. So VD voltage will be again VDD minus IDRD because source voltage is 0. So VDS is actually equal to VD voltage also. Okay. So let's solve a numerical on it quickly. So let's say that the values are given. RD value is 1.5 kilo ohm, VDD is 20 volt, RG value is 1 mega ohm, IDSS is 10 milliampere, VP is minus 4 volt. Okay, you need to find the Q point. Find Q point and VDSQ. So please do that. So first write down, you write the numerical over here, solution, and supply voltage is 20 volt. Supply voltage is 20. So first write down VGS Q is 0. Second step, IDQ is equal to IDSS, right? That is equal to 10 milliampere. Third step, Q point is VGSQ comma IDQ, which is 0 comma 10 milliampere. Fourth point, what is VDSQ? VDD minus IDQ into RD. So calculate this number and tell me. It is 10 raised to minus 3 into 1.5 into 10 raised to 3. So how much is this? 5 volt, right? Please cross check. Hello. Can you cross check this number? Anyone got these numbers correct? Hello. Did you all get these numbers? Can I move on?
Yes, sir.
Okay, great. Okay. So next we go for self bias circuit. Self bias circuit using NMOS D type MOSFET. So this I'll only solve the analysis, numerical I'll skip. I've already shared the PDF, you can refer it. Okay, I'll only discuss the circuit. So here we draw the symbol first. Okay, so the three terminals are gate, drain and source. So here you have RD, here you also have RG, but here you also have RS. So RS is the additional term. This is RG, yeah. So this is the circuit. Now over here I'll mark certain things. This is VGS. Current over here is ID. Here this is VDS. And here IG is flowing but it's 0. We know it's 0. Why it is 0? You write it down. Okay? Ready? So for these cases, your VGS will come out to be negative, right? This circuit is for VGS equal to negative. Let's see why. Okay, can we start? And also remember the current ID and current IS are one and the same. So ID drain current and source current are same. So we can write interchangeably. So let us start by applying first KVL to gate source loop. So when we apply KVL to the gate source loop, what do we get? Yeah, here same thing we get. So we'll get minus IG RG minus VGS minus IDRS is equal to 0. Did you understand how do I write this equation? I minus IGRG minus VGS minus, instead of ID, IS, I'll write ID RS. Is this understood? But Ig is 0 because of SiO2 layer, silicon dioxide layer. Okay. So what do we get VGSQ as? Minus ID RS. So Ig VGSQ is negative. See, that's what we want. Got it? Everyone understanding? Once we know the value of VGSQ, we'll find the value of IDQ as IDSS into 1 minus VGSQ upon VP the whole square. Okay, so we get the value of VGSQ and IDQ. Now we have to calculate VDSQ. So let's apply KVL to drain source loop. Okay, so drain source loop is over here. I'll mark in green blue color like this. So it will be VDD minus IDRD minus VDS minus IDRS is equal to 0. So let's write it down. It will be VDD. Okay. It will be VDD minus ID into RD minus VDS minus IDRS is equal to 0. You follow this blue color. Okay. So VDD minus IDRD minus VDS minus IDRS is equal to 0. So from here, club all the terms of VDSQ together, and your VDSQ will be VDD minus ID into RS plus RD. Okay. Are you following up till here? I mean, you all are following what is going on?
Yes, sir.
Okay. Um, Now we go for voltage divider biasing. Now I'll skip the numerical for this self bias circuit. I'll go for the numerical for voltage divider biasing. Okay. So let's start. Let's commence. So write the third one as voltage divider biasing. Remember, voltage divider biasing is both for D type and E type. So be very careful in the numericals if it comes. Okay. So let's begin. You remember BJT voltage divider biasing is similar, but here you have a MOSFET. So draw the MOSFET symbol. So we have RD, RS, and then we have a voltage divider. What is a voltage divider? R1, R2. And you take that from VDD. This is VDD. Okay. So this is R1, R2. These are joined together towards ground. So please make this circuit. Then mark gate terminal, drain terminal, source terminal, VDS and ID. Do you remember what do we do next in voltage divider biasing? Anyone remembers? We apply Thevenin's theorem at gate terminal of MOSFET. So that means we are applying Thevenin's theorem over here. Okay. So when we apply Thevenin's theorem at the gate terminal, how much will be my, here it is, this is the one. Between gate and ground. Gate and ground. This is VDD. So can you tell me what will be, this will be converted into a single voltage source in series with a resistance between gate and ground. So this will be RTH and VTH. Can you tell me what is the value of RTH, VTH over here? Anyone? What is RTH? VTH over here, it will be R2 divided by R1 plus R2 into VDD. And what will be RTH?
R1 parallel to R2.
Yes. This is same as your BJT. Okay. Now we draw the equivalent circuit. So instead of R1 and R2, you will have a new circuit now. So let me draw that. And oh, sorry, let me draw slightly below. So you have RTH. Up till gate terminal, everything changes before gate terminal. After that, everything is same. So draw the MOSFET back. Draw its symbol. Draw RD, VDD, and RS. Got it? Now in this circuit, you apply KVL and KCL. So I'll apply KVL to first to this loop. Okay, first of all I have to mark certain things. This is current IG, this is VGS, this will be VDS, and this will be ID. Why it is important to mark these things? Because or else you will forget. While writing you will forget it. So now we'll apply KVL to gate source loop. So what do we get? Can you tell me? VTH, this is minus plus, VTH minus IG into RTH minus VGS minus IDRS is equal to 0. Okay, but here what do we write? IG is equal to 0 because of presence of oxide layer. Okay, then what we left out with? What is VGSQ now? Tell me. VTH minus IDRS. Got it? Hello, you all are following?
Yes, sir.
If VGSQ is this, what is IDQ? IDSS 1 minus VGS upon VP the whole square. So you have VGSQ, you have IDQ. Now only thing left out is VDSQ. So for VDSQ, what do? You apply KVL to drain source loop. Let me draw the drain source loop for you. This is my MOSFET. Okay, only drain source loop. I'm not interested what is connected at the gate terminal. This is RS, RD, and this is VDD. Okay. If I'm going too fast, please let me know. I'll slow down. This is VDS, this is ID, and this also is ID. Now tell me, what will be the value over here? You're going from VDD to ground. So it will be VDD minus ID RD minus VDS minus ID RS is equal to 0. So what will be the value of VDSQ? Will be VDD minus ID times RD plus RS. Got it? Okay. So these are the expressions. Did you understand? Hello?
Yes,
Yes,
sir.
sir.
Actually, this is analytical method. Whatever we are doing, this is analytical method to solve. This is analytical method. Okay. There is graphical method also. Now graphical method I am not teaching right now. I'll show you the graphical method just once for every technique. But I am not covering in today's session. You can refer it. So see, this is what we have done now for cell bias circuit. So we can determine this graphically also, Q point. But it's I don't know whether it's been covered in B division, but A division I have covered it in my class. So you can you can refer it and see whether you can understand it. Okay. Right now for the completion sake, and we have less time, I'm skipping this part and directly jumping to numerical, because numerical you can solve it using analytical or graphical. Okay. So can we start with the numerical now for this depletion type voltage divider biasing? Yes or no?
Yes, sir.
Okay. So let's start with numerical number 1. Find VG, find VGS, ID and VDS for circuit shown below. Okay, so please draw the circuit. So draw the voltage divider biasing. Okay, this is my gate terminal, this is my VDD, R1, R2, RD, RS. The values given are as follows. R1 is 110 mega ohm, R2 is 10 mega ohm, RD is 1.8 kilo ohm, RS is 750 ohm, and the D MOSFET parameters are D MOSFET parameters. Given values are IDSS is equal to 6 milliampere, Vp is equal to minus 3 volt. This is the given data. How will you solve this? I mean, you can convert this into Thevenin's equivalent, but if you know the result, it's fine. Or else in the exam, if you forget it, just draw the Thevenin's equivalent of it. That's it. And then you can derive it. So I'm just quickly drawing it. It's not necessary for you to draw. It's not at all compulsory if you know the formula. So if you don't know it, then you can derive it very simply by drawing this network. So I'm not doing the derivation again. We have already done that right now. This is RD, RS and VDD. So from here, tell me from the last analysis, what is the value of VTH? Tell me. VTH is R2
R2.
upon R1 plus R2 into VDD. Yeah? So substitute the values, please. So it will be 10 divided by 110 plus 10 into VDD value is 18 volts into 18. So can you tell me how much is this?
1.5.
Yes, it's 1.5, correct. Then no need to find RTH. Huh? So find what is VGSQ? We got it. It's VG minus ID RS. Yes or no? Or VTH minus, sorry. You have written a VTH minus, right? ID RS. Just check. See, VTH minus ID RS. Who wants to join the meeting? Okay. Okay, fine. VGSQ is VTH minus IDRS. How much is VTH? 1.5. How much is RS? Anyone? 750 it is. So this we call it equation number 1. Okay. Then we say, assuming given device is in saturation region. We have to write this statement. Then we can write as follows. Then we can say IDQ is given by IDSS into 1 minus VGS upon VP the whole square. And what is IDSS given as? 6 milliampere, 1 minus VGS upon, how much is VP given? Minus 3. So if I substitute minus 3 over here, this will become plus square. Did you get it? I mean, did you understand how do I write, how we have written equation number 1 and 2? Anyone, any doubt? Because I am writing very fast. See, you have to understand it and then write it. You have any doubts over here, or else shall I proceed? Hello?
So you can proceed, sir.
Okay. Now always remember, your student make a little bit trouble for themselves. Always put equation number 2 in 1. Never put 1 in 2 because it will land up into more steps. So always put this expression number of IDQ in 1. Okay. So let's do that. So we are doing it live over here. Wait a second. It is let it be a little more clear. Yeah. Is it clear now again for you all? Okay.
Yes, sir.
Now, fourth one is putting 2 in 1. So we'll write down two equations. VGSQ is equal to 1.5 minus IDQ. What is IDQ? 6 milliampere into 750 into 1 plus VGS upon 3 the whole square. Got it? Now you have to solve this quadratic. So it is 1.5 minus, this is 4.5, this is a plus b square. So a square plus 2ab plus b square, which is VGS square upon 9. And now you open the bracket. VGSQ is equal to 1.5 minus 4.5 minus 3 times VGS minus 0.5 VGS square, or Q you can write, or you can skip the value of Q over here, VGS. Okay. Then you will get a quadratic equation in VGS. So that will be 0.5 VGS square plus 4 VGS plus 3 is equal to 0. Please check whether you are getting this much. This is just mathematics now. To solve this in your calculator and let me know the value of VGSQ. Two values. You will get two values of VGSQ. Yeah? What is VGSQ? Anyone?
It's a 7.16 minus 7.16, sir.
And second value?
And second one will be
0.
minus
8372.
837.
Okay. Now which value is correct? See, this is my graph. This is my ID versus, this is VP. This is VGS. This is ID. This is IDSS. This value. Okay. This is IDSS. Now VGS has to be greater than VP. So if VP is, let's say in our case, how much is VP? Minus 3 now. How much is VP? Minus 3. And what is the value of VGSQ we are getting? Minus 8.77. So it's well within this, right? So VGSQ is greater than VP. That's why we select this value. And why do we reject this? Because if I plot minus 7.16, it will go beyond this, right? And no point is defined. Are you understanding what I'm saying?
Yes, sir.
VGS cannot be greater than less than VP. It has to be greater than VP in a negative direction. So once I have selected the value, so this is my value of VGSQ. Now find the value of IDQ immediately. So IDQ will be IDSS 1 minus VGSQ upon VP the whole square. So be careful here also. IDSS will be 6 into 10 raised to minus 3 into 1 minus. See, this is minus over here, right? Minus 0.8377 divided by VP is also minus 3. So be careful in this calculation. So calculate IDQ. How much is IDQ? Anyone? Anyone with the value? And remember, it is square. It will be milliamperes. Please tell me quickly so that I can.
5.53 milliamperes.
No,
Right?
no.
3.11
Yes, that's
milliamperes.
correct. 3.11 is the correct answer. Please check your calculation once. Got it? And what is VDSQ now? VDD minus IDQ into RS plus RD. So this is 18 minus 3.11 milli into 750 plus 1.8K. So calculate this VDSQ. This will be around 10.07. Just cross check these answers. Is it coming as 10.07 VDSQ?
Yes, sir.
Okay, great. Okay, so we have completed the depletion type MOSFET, biasing and numericals. So 60% of the lecture is over. Now we have to go for enhancement type MOSFET biasing. So are we ready? Everyone ready? We'll go for NMOS enhancement type biasing circuits. So for NMOS type enhancement biasing, we know VGS has to be greater than VTN. That means VGS can only take positive values. Remember, in a depletion type, VGS can take 0, negative and positive value, but in enhancement type NMOS, it will take only positive value. Okay, why? Because if we check the graph of transfer curve, it will look like this. Okay, this is ID versus VGS. And what is this expression given by? What is ID given by over here? ID will be given by Kn VGS minus VTN, the whole square. So yeah, so once we get the value of VGS, we can calculate the value of ID using this formula. And what are the types of biasing techniques? And again, we fix the Q point over here and calculate VGS Q, and here we calculate IDQ like this. This is my Q point. Okay, what are the types of biasing? First is drain feedback bias. Second is voltage divider bias. So can we start now, everyone, with drain feedback bias? Okay. So write down drain feedback bias. So it's similar to collector to base bias in BJT. Okay, and here we are using NMOS E-type MOSFET. So it's not possible in D-type MOSFET to have drain feedback bias. So what is the symbol? Like this, dotted line. Dotted line indicates that a channel is not formed yet. Okay, so we have RD register, we have RG register, but RG, instead of going to VDD, it will go to drain terminal. Alright, and here this will go to the ground. Okay, I hope you are following. This is VDD. Let me save it. Yeah, this is RD and this is RG. I have to write additional things. This is the drain terminal, this is the gate terminal, this is VDS, this is VGS. Current over here will be ID. Will the current be ID over here? Anyone remember? I mean, can tell me?
So IG plus ID होगा ना?
Yes, perfect. Because I know the IG current is 0, but still IG, let's say IG current flows over here. Let me just this thing, pen tablet is little bit misbehaving. Let me connect it again. Yeah, I hope so. It's connected now. So my IG current is this direction. Okay, so this will be IG plus ID, and this current will be ID. Got it? Did you understand what we have written? Hello? Understood this?
Yes, sir.
Okay. Now we apply KVL to gate source loop. So what is my gate source loop? From here to here. So tell me what will be the equation? VDD minus IG plus ID into RD minus IG RG minus VGSQ equal to 0. But what do we know for a MOSFET? IG is equal
IG
to
is
0
0.
because of the presence of oxide layer. So it will be VDD minus ID RD minus VGS is equal to 0. So how much is VGSQ now? VDD minus ID into RD. That is the expression of VGSQ. Got it? Now once we know the value of VGSQ, we can find the expression of IDQ easily. So IDQ will be Kn times VGSQ minus VTN, the whole square. Correct? Okay. Now we apply KVL to drain source loop. So where is my drain source loop over here? Anyone? This one, the one in blue color. So what do we have over here? Can anyone tell me? VDD minus IG plus ID into RD, or we can directly write ID RD minus VDS is equal to 0. Yes or no? So here we'll write VDD minus, I know IG is 0, so ID RD minus VDS is equal to 0. So how much is VDSQ? Got it? If you note one thing, this equation is same as this equation. They are one and the same. Okay? Because gate terminal is almost tied to the drain terminal, because current through the resistor RG will be almost 0, so there will be no voltage drop. So that's why it is called as a drain feedback bias. Understood this, everyone? Yeah?
Yes, sir.
Okay. So next we'll solve a numerical on drain feedback bias and then followed by voltage divider bias. So that will be the last topic. So write down numerical number 3, right, for today. So write down, find VGS, ID and VDS for circuit shown. So draw the circuit please. This is dotted line. Whenever that is there, it is enhancement type MOSFET. So here we have a resistor. Drain feedback bias is very unique circuit. You will identify very fast. And this is grounded. This is VDD, RD, RG. The values are, RD value is 2K, VDD is 12 volt, RG is 1 mega. And they have given NMOS E-type data. Parameters are given. So ID on is given as 6 milliampere. VGS on is given as 8 volt. VGS TH is given as 3 volt. This is the given data. Have you completed? Hello? Yeah, students, completed up till here? This is gate,
Yes, sir.
drain and source. Now let's start with the solution. Okay. So actually ID on, VGS on and VGS TH on is basically given by this formula. We can find Kn from it. So Kn will be ID on divided by VGS on minus VGS TH the whole square. So please note down this formula. Kn is ID on divided by VGS on minus VGS TH. So this is 6 milliampere. So 6 into 10 raised to minus 3 divided by VGS on is 8 minus VGS TH is 3. So tell me how much is this? It will be 0.24 milliampere per volt square. Please cross check this answer. Whatever answer you are getting, converted into milli. Is it 0.24 milliampere per volt square? Six divided by 5 square, that is 25. So it is 0.24 milli because it is 10 raised to minus 3. Did you all get this value?
Yes, sir.
Ask.
Okay, got it. Next, let's calculate VGS. Okay, if you forget this, you can derive it, but you know VGSQ is given by VDD minus ID RD. Just now we have seen now VGSQ is VDD minus ID RD. So calculate this. This will be 12 minus ID times 2000. RD is 2000. This we call it equation number 1. Then we write a statement that assuming given device is in saturation region, hence we can write IDQ as Kn times VGS minus VTN the whole square. So this will be, what is Kn? 0.24 into 0.24 into 10 raised to minus 3 VGS minus VTN. What is VTN? VTN is same as this one. This is also called as VTN or VTH or VGSTH. They all mean the same. So this is OR. So how much is it? 3 square. So call this equation number 2. Now what do we do? Put 2 in 1 or 1 in 2? Can you all tell?
2 in 1.
Yeah. Put equation number 2 in 1. So what do we get? VGS is equal to 12 minus ID. ID is 0.5, 0.24 into 10 raised to minus 3 into 2000 into VGS minus 3 the whole square. Got it? Now you have to simplify this algebraically. So it is 12 minus, this will be 0.48 into a square minus b square. So a square minus 2ab. Okay, this will be 6 plus b square. Okay. Now we open the bracket. So it will 0.48 VGS square plus this will be 2.88 VGS minus 4.32. So please cross check the quadratic equation now. 0.48 VGS square minus 1.88 VGS minus 7.68 is equal to 0. So solve this to get the values of VGSQ. So you will get two values of VGSQ. Tell me which is correct. Both the unit will be in volts. Remember, this is enhancement type biasing. Hello? The answers, please. How much is VGS? Q?
6.41
And?
and minus 2.49, 2.5.
Yeah. So we reject this, we select this. Why? Because VGS should be greater than VTN. And VTN is 3 volt. So it cannot be negative. That's why we select that value. Okay. So next we can calculate D. IDQ. So IDQ will be Kn times VGSQ minus VTN the whole square. That will be 0.24 into 10 raised to minus 3 into VGS is 6.41, VTN is minus 3 the whole square. So calculate this IDQ. It will be 2.79 milliamperes. Please check this value. We have to find VGS, ID and VDS. Okay. Did you all get this value?
Yes, sir.
Okay. So remember, in drain feedback bias, uh, VGSQ was equal to VDSQ, right? And that is equal to, we got the value as 6.41. So last step is this only. Because we have seen over here, right, in the derivation, that VDSQ and VGSQ expressions are same. So we can equate them over here. So VDSQ is 6.41. That's it. That's the numerical. Got it? Can we go for the last one now? All of you got the answers? Last one is remaining, voltage divider bias. Can I start?
Yes, sir.
Okay. Uh, Voltage, I will be little quick now because this is repeated for the third time. Voltage divider biasing for NMOS E type. Okay, so what is my, draw the circuit first, but this time draw the symbol for enhancement type MOSFET. Okay. So it's the same configuration as depletion type, only the MOSFET is enhancement type. R1, R2, RD, RS and ground. So this we apply Thevenin's theorem at gate terminal. So what do we get? VTH, RTH, this is RD, this is VDD, this is RD, VTH, RTH. And all the analysis is exactly similar. This is gate, source and drain. Sorry, this is RS. Okay. Then we apply KCL in the KVL in the gate to source loop, the yellow color. Then next case we apply KCL in the drain to source loop. We have done this many times, so I am not repeating again. I am directly writing the expressions for VTH. What it is? R2 upon R1 plus R2 into VDD. What is RTH? R1 parallel to R2. Acha, what is VGSQ? Same, it will come same. VTH minus IDQ into RS. We can check it out. Okay, but over here, what is different is this is different. In depletion type, the formula for IDQ was different. Here it is different. It is Kn times VGSQ minus VTN, the whole square. So this is the difference. This is the difference in formula for E-type devices. Got it? Only this step is different, rest all the steps are same. Similarly, if we analyze further, we have done that for depletion type. VDSQ will be obtained by applying KVL to the drain source loop, and that will be VDD minus ID times RD plus RS. So I don't want to repeat that. Is it fine? Because it's the same steps. Only I told you what is different, IDQ is different, that's it. Rest everything is same. Did you all get it? Hello? Hello?
Yes, sir.
Acha, okay, fine. So we will solve one numerical on voltage divider bias and we'll call for today. That will be the last numerical for the day. So let's do it together. So first of all, write the question, numerical. This is the fourth numerical, I guess, for today. Yeah. Find VGS, ID, VDS for circuit shown below, and find the region of operation of given device. So what is that given device? This is the MOSFET. So let's draw the diagram first. So this is the MOSFET. It is voltage divider bias. This is VDD, R1, R2, RD, RS, and ground. Now no need to, if you don't directly the formula, that is fine, or else convert it to Thevenin's equivalent and all that. What is the given data? R1 is 22 mega ohm, R2 is 18 mega ohm, this is 820 ohm, RD is 3 kilo ohm, and NMOS E type parameter are VTN is 5 volt and Kn is 0.12 milliampere per volt square. Okay, this is the given data. Now we have solved voltage divider bias many times, so I am skipping some steps. But if you are confused, then you can draw it again, the Thevenin's equivalent circuit, and then solve it. So what will be VTH? Acha, what will be VDD given over here? 40 volt. So VTH will be R2 upon R1 plus R2 into VDD. So that will be 18 divided by 40 into 40. So actually 18 divided by 18 plus 22. So that will be 18 volt only, right? Got it? No need to calculate RTH. Then calculate VGSQ, which is VTH minus IDRS, which is 18 volt minus ID times RS is 820. So this is equation number 1. Now what do we write next? Assuming given device is working in saturation region, correct? Then what formula do we write? IDQ is equal to Kn times VGSQ minus VTN the whole square. So this will be 0.12 into 10 raised to minus 3 VGSQ minus 5. This is VTN is 5 volt. So this is equation number 2. Now there are formal steps. Put equation 2 in equation number 1. We get VGSQ is equal to 18 minus 820 into 0.12. We are writing the expression for IDQ. Okay, into 10 raised to minus 3 VGSQ minus 5 the whole square. Got it? Now we simplify it further. VGSQ will be equal to 18 minus 820 into 0.12 into 10 raised to minus 3 will be 0.0984. Please cross check. A square a minus b the whole square will be a square minus 2ab minus 10 VGSQ plus 25 equal to 0. That will be VGSQ is equal to 18 minus 0.0984. Please confirm this number. Plus 0.984 times VGSQ minus 2.46. Are you getting these numbers correct? Can someone reply? So the quadratic equation will be VGSQ square plus 0.016 VGSQ minus 15.54 volt is equal to 0. Are you all getting this quadratic equation? Please let me know. Or you are facing any difficulty? Hello? Everything all right? I mean, quadratic equation is similar. So find the value of VGSQ and let me know the answer. How much is VGSQ? Anyone?
12.48
Yes.
and minus 12.64.
So which value you will reject? This one. And this value you will accept. Why? Because VGS has to be greater than VTN. So VGS equal to 12.48 is the correct answer. And after finding this, you find the value of current. So current is given by the formula IDQ is Kn times VGS minus VTN the whole square. Kn is 0.12 into 10 raised to minus 3. VGS is 12.48 minus VTN is 5 square. So please calculate IDQ. This will come out to be 6.72 milliampere. Please cross check this number. Did you get this?
Yes, sir.
Okay, one last step, second last step. Next, calculate VDSQ. That will be VDD minus ID into RD plus RS. That will be 40 minus 6.72 milli into 3K plus 820. So calculate this. Okay, what happened? Okay, got it. Calculate VDSQ. It will be 14.32. Anyone got 14.32? Yes or no? Is this value correct? 14.32 VDSQ. Yeah, anyone with the answer? Can someone let me know? Is this matching?
Sir.
Okay. Now we have to find the region of operation. Last step. We need to find region of operation of device, of given device, and given device is NMOS E-type MOSFET. Okay, how do we do that? Number one condition to check is whether VGSQ is greater than VTN. So is it true? VGSQ कितना है? 12.48. Is it greater than 5 volt? Yes. So this condition is satisfied. Okay. What is the second condition? If VDSQ is greater than VGSQ minus VTN, just check that. VDSQ कितना आया? 14.32. Is it greater than or less than VGSQ, which is 12.48 minus 5? Is it happening?
Greater, yes.
Yes. So if these two conditions are satisfied, then what can we say? The given device is indeed working in saturation region. So yeah, that's it. So this is what we were supposed to cover till today. We have completed module number 2.2, all the topics in it.